Hello, my name is Samir Hernandez, and this is my Evidence2. Well, I will begin with discrete time state space models, and these are control systems based on a matrix that contain the states of the system, like like dynamics and actuators. And this system takes samples of the states every certain time t. And this last time property is what differs a discrete from a continuous time system, because a continuous time system has a value for every instant instead of a sample every certain time. Now, a state space, a state feedback with observer is simply a controller in which a observer should be designed to work with the output signal Y, and the signal obtained from the observer must be fed through a state feedback matrix to complete the controller. Now, the procedure to design a state feedback controller with observer is this one. First, you need to check that the matrices that we are using from the beginning will provide an observable and controllable system. For this, we can use the MATLAB functions CTRB and OBSV, that are these ones here. And by comparing the rank of the obtained matrices to the value n, we can determine the observability and controllability. Then we need to analyze and shape the poles of the base model so that all the poles are inside the unit circle. These are the poles I used for this evidence. The poles here in line 43. These are my poles. And well, now using the function place, we can generate the state feedback gain matrix by introducing the A and B matrices along with the poles list in the function. This procedure is right here. And this matrix obtained is commonly known as K. Okay, now finally, we can generate the state matrix for the system with the function SS that takes the A, B, C, and D matrices along with the TS constant. And this will provide the matrix that will make the system work. Now, how should the closed loop poles be chosen? This procedure is very simple, because we just need to take the poles outside the unit circle back in, and then we must play with the real and imaginary parts of the poles so that we can reach the desired performance of the system. In terms of, well, by solving this evidence, I could see that in terms of increasing damping, we should decrease the imaginary part, and for increasing speed, we should decrease the real part. Now, I chose these poles because they meet the requirements for the evidence. First of all, the closed loop system should be stable, and my poles provide a stable system because all of them are inside the unit circle, so the system is stable. Also, we can see that the stability in this graph, the continual position, we can see that the signal a long time becomes steady, becomes constant, and has few oscillations, nothing to becomes unstable. Then we need to check for the bandwidth. The bandwidth should be at least 0.2 radians over second. This property can be confirmed by this one, the body plot. Here is hard to see, but I checked this body plot, and my bandwidth is between 0.3 and 0.4 radians over second. So my system meets this requirement. Now, going to the next one, the settling time should be less than 30 seconds. 30 seconds, okay. We can check this in the previous image. We can see that my system settles about 13 seconds, 13.48 is more or less the settling time. And it's obviously less than 30, so fast response, good performance. And finally, we have the signal, the input signal should not exceed 40 kilonewtons. And this can be seen in the trolley force. Here we just have to check the peak. And the peak here is under 40 kilonewtons. So the system meets this requirement too. So it's a good performance, good system. it meets the evidence requirements perfectly. And this brings me to the conclusion. In conclusion, I could say that the most valuable knowledge I take from this course is working with discrete time systems, because these are the most commonly found systems in real applications, and this fact makes this topic fundamental for our future professional lives. Thank you very much.